I'm going to talk about something which is really hot, a really hot topic today, which is water in planets. It's very hot for the moon. It's still a big debate for the Earth. Now we will probably learn very soon how much water was in the moon, in the Earth, something like 2 billion years ago or 2.5 billion years ago. But I'm going to talk about this difficult problem. So, you know about water. Water is important for life. It's a meeting on astrobiology here. And today we know that water is NASA's motto. Look for water and you will find life, which is probably totally wrong. Because what you need for life is not only water, but it's also continents. Here, what you have is evidence that's a productivity, the oceanic productivity. You see that productivity is associated with what? With essentially the continents here in red. You also have some upwelling, like subequatorial upwellings here, or in these places here, but essentially we need continents. So water is something important, but in relation to continents, simply because if there is no continent, there is no nutrients. You cannot renew the nutrients. This is why I'm not a firm believer in the planet ocean and things like this, because you need to replenish all the nutrients. What is the effect of, we heard a little bit about this yesterday, what's the effect of water on the dynamics of a planet? Here is a very nice picture by Paul Tackley, which was published something like 15 years ago. And the effect of water on interior of planets is to reduce viscosity and reduce tensile strength. It reduces the amount of strength you need to apply to a body to break it. And in that slide, Paul emphasized two things, two types of behavior that we heard about yesterday from Tillman. If you have a planet like Mars that most of us consider as relatively dry, you have a regime of stagnant lid here, and you have this kind of shape for convection here. To the Earth, which is reasonably wet, and here you have different, what they call plant form. You have subduction zones, you have plumes, you have things like this, and you can maintain plumes. So if there is water in the planet, we can hope that there's going to be some plate tectonics, and we can hope that we're going to get continents, the dichotomy of continent and ocean. We're going to have a subaerial continents discussion we had at the end of Tillman's talk yesterday. If we have a continents, we might have a rivers. River will bring phosphorus and other nutrient to the sea, and life has a chance of surviving. Otherwise, if there is no continent, life is like all my kids. They eat whatever is in the fridge, and then when everything is gone, everybody's starving, and this someone's resupply the whole thing. In order to understand the logic of water in planets, we have to go back to something very simple, which is the composition of the solar nebula here. We have to realize, okay, there is plenty. You will hear me talk about water as an element. It's actually hydrogen, which is the most important, okay? But for short, hydrogen doesn't sound very appealing, so I'm going to talk about water as an element. If you look at the composition of the photosphere, this is what you have here. You have a solar photosphere, which is essentially composed of hydrogen here, a little bit of helium, and nothing of the rest. Okay, this is that's the sun. That was the composition of the solar nebula when it formed. It was dominated by hydrogen. Okay, that's something. And the rest, you'll find all the elements that you normally find in chondrites. Chondrites, You remove the blue and the red, and then you're going to have a chondrite, carbonaceous chondrite. So, and we're going to talk about a volatility scale. You know, everybody thinks of water as a volatile component, a volatile element. And so we have to define, we're going to come back to this point a number of times, what the volatility scale means. We have it. But essentially, you can use, it is relatively simple to use that kind of concept here that goes back to 50 years ago, even more. It actually goes back to Howard Urey one more time. You have this kind of reaction here, magnesium in gas reacting with silicon in the gas. At a high temperature, silicon is in the form of SiO. So just like a carbon is in the form of CO, silicon is in the form of SiO. So you have that kind of reaction between three gas components, magnesium, silicon oxide, and water here, reacting to form a solid that you will call forsterite, which is an olivine here, and leaving behind some hydrogen here. So you can write an equilibrium constant for that reaction, and you see that the most important aspect is that hydrogen pressure is a component of essentially every reaction here. So you have this equilibrium component here. You see this P cubed H2, and H2, as you could figure it out from the previous slide, is essentially the total pressure. That's the total pressure because the solar nebula is made essentially of hydrogen. So you can actually define some energetic equivalent of this equilibrium constant and derive some kind of literature from thermodynamic properties here. So we can then we can play that game taking the solar nebula, assume that it's warm or it's hot. It's hot, why we learned it yesterday from Cedric that everything condenses, so we recover some gravitational energy, converted it into kinetic energy, which most people call temperature, so it's hot. And then the material spread in a sense and expands, so it cools down. So there is no secret about this. And there is a condensation of the material. We start out with the gas, and by cooling down, we're going to precipitate, we're going to condense a number of solid phases like forsterite I was just talking about. And if you do that, which has been an exercise many people did in the 70s, this is the temperature, this is the fraction condensed. Okay, here. You go from 0 to 100%, something is missing here, it's going to be the volatile part. But the main feature here is a fraction of condensed of the condensable material. If you remove hydrogen and helium, you calculate how much can be condensed. Hydrogen and helium cannot be condensed except in the outer solar system. So it looks like this. You have this ultra high temperature, ultra refractory material here. This is temperature in Kelvin here. You have this ultra high temperature refractory material, which is plagioclase, clinopyroxene, and totally unsexy phases like hebonite, and you don't want to talk about the melilite, and you don't want to mention that. And you see that it precipitates relatively fast over a small temperature interval here, and then, but not too fast. And then all of a sudden, over 100 or 150 degrees C, all the material forming the planets precipitates extremely quickly. That's something to remember. There is gas, and all of a sudden, you have everything you need to make the mantle and the core of planets over a temperature interval of 100, 150 degrees. So we precipitate 65 or 70% of the material over a temperature interval of roughly 100 degrees. And then everything comes to the grinding halt here. Nothing precipitates for a while. Okay? except a few elements that are of interest for us, like alkali elements, and we have also some sulfide some what we call chalcophile or sulfide-loving elements like copper. Okay, they precipitate somewhere here, but essentially this is nothing. Between 1200 degrees, the 1200 K and 700 K, there isn't much action here. There is nothing. And all of a sudden, by 700 degrees, we start having sulfur precipitating. And some other volatile elements like zinc, cadmium, thallium, you name it, okay? And then it comes to here to 75%, 77%. You're going to say, where is water here? Where is hydrogen? Hydrogen is nowhere to be seen. We don't see carbon, we don't see nitrogen. Because they're missing. They're somewhere down by the heater here, by the heating here in the bottom. So it means that the condensation is a very discontinuous process. If the process stops here, chances that you're going to see a material volatile. That's what you remember. If condensation stops at, let's say, a good number for the Earth is 1100 K, chances of having water in the Earth is nil, because we are down here. We haven't even thought about condensing water at that point. So, and that happens very fast. This is a very nice diagram. You see, this is essentially the same plot as the previous one, fraction of element condensed versus temperature here. This is the same plot with except it's a log scale. This is 10%, this is 15%, and each element here condenses over a very narrow temperature interval. Very, very narrow, okay? And you have this famous or infamous T50, the temperature at which 50% of the element is condensed, which has been used for 50 years as a measure of the element volatility here. There's a T50, that's 50% of the element. But you can see that condensation goes extremely fast. There are some exceptions here. You essentially, the exceptions are the alkali elements, but not much, and elements like europium, ytterbium, because they have some very specific electronic properties. You can actually, you want to look smart, you apply some statistical mechanics, and you can calculate the, the temperature interval here. You can, with the number of elements remaining in the number of atoms remaining in the vapor, and you can define a temperature interval here of an average condensation temperature interval of 20 to 50 K, with exception of 150 K for alkali elements that have some degenerate electronic states. So we can define a condensation temperature just to show you that it was not a recent concern. This is by Larry Grossman for his PhD in 1972, defining a series of condensation temperature, T50 if you like it, from 1758 here to, and you see all the Earth or the planet forming elements here condensing between 1000 and 1300 K, like anortite, enstatite, I don't know what escolite is, but and metals are somewhere. Diopside is a pyroxene, metallic iron. You see how it goes. And the most famous attempt of them all is the scale published by Cathy Lodders in 2003. This is a nice periodic table she published in an ABJ paper. Let's do it again. And you see different colors correspond to different geochemical properties. In green, you have, in bright green, you have lithophile elements like magnesium, potassium, whatever forms the silicate part of the planets here. In blue, you have a siderophile or iron-loving elements, like iron, of course, but also nickel, cobalt, and the platinum group element here, ruthenium. We're going to go back to this element, rhodium, palladium, platinum, iridium, osmium. These are platinum group elements. And you have some other elements like germanium, arsenic, or whatever. And you have this temperature scale here, which is in red. So you see that the most lithophile elements are refractory, but some of them are volatile, like zinc, like lead is slightly, it's a different cases here. But you have some volatile elements where they probably zinc, well, these are kind of chalcophile here, and we have that scale here. So what you have to remember, and that's, I will not insist enough on that point, is that condensation temperature is not a vague, smooth, broad, and wimpy scale of temperature. You have a refractory element here. Then you have a first gap here. You have alkali and high temperature chalcophile elements here. Then another very nice gap. And low temperature chalcophile elements, zinc, lead, or whatever. And then you have a big gap here, and sulfur is somewhere around here. And then you have a carbon, nitrogen, hydrogen, water. You have all these elements here. So if condensation stops here, there is no way you're going to see anything in the Earth, for instance. If the Earth stopped or the Moon stopped condensing here, you're not going to see any water. So the idea of having primordial water in a planet that is overall depleted in volatile doesn't make sense, even though this is something which is extremely common in the literature. It makes no sense for that reason here. So, can we treat water in a different way? Yeah, we think that water is something magic, and it's not. It's not. People think, oh, water is life, water is something I use to take a shower every day, you know, something really magic. I'll cook the food and whatever you want. And until I realized, it was 3 years ago in Iceland here, I made that plot that made a number of people unhappy. You know, there were a number, I'm going to come back to this point, that water had to be treated in a special way because water makes ice. And so you can play ping pong in the solar nebula by moving ice, and then you move rocks, and you move things, and you fractionate essentially water from rocks, and that doesn't fly. Why? Look at this. You plot water here versus zinc in meteorites and in different planetary objects. Why did I divide by calcium? It's just because when something evaporates from a medium, it is volatile. You know, just by mass balance, the amount of refractory material increases. Decrease the amount of volatile, you will increase the proportion of refractory element. So this is normalized to a highly refractory element, which is calcium. And here you have this wonderful correlation here. Don't tell me that water is anything special. It's no more special than zinc. It is special at the surface of the planet. It's special under some condition, but it's not very, very special. The special property of water is to have a low molecular weight. You know that, for instance, crystallization temperature changes with the number of a particular component added to a mixture, for instance. Okay, you take a basalt and you add some potassium, you add water, and the extent to which condensation is, the temperature of condensation is decreased, is proportional to the number of moles, not to the weight. So water has a low molecular weight. In this respect, it's a very efficient way of changing the properties of medium is by adding a component with a low molecular weight. That's the property of water. Same thing for carbon. Don't tell me that carbon is any special. Carbon follows zinc. Zinc is a boring element. Everybody gets excited with zinc now. Okay? And you see that carbon and zinc follow each other. So all these elements are very consistent. Every theory that wants to deal with the water content of planets, of planetary objects or whatever, has to deal with the fact that you cannot dissociate water from other volatiles or less volatile elements. This is a very basic fact here. So now let's look at a very simple way of of understanding the solar nebula. This is the sun. The sun radiates some energy here. Here, this is photons with energy here. The amount of energy, it could be a sphere, but here is a circle, doesn't make much difference. The amount of energy that crossing the red, if there is no opacity, the amount of energy crossing every circle is the same. So the energy density, energy per square meter here, is much smaller here than here. That's something you figure out when you are in your bathroom and you have this heater here. If you get close, you get fried. If you get too fast, you get too cold. Too far, you get too cold. That's exactly the same idea, and that gave rise to the concept of what people call snow line, frost line. You have different ways here. And the sun is here, and we think that inside it's pretty hot. We are right next to the heater called the sun, and in the outskirt of the solar system, in the outer solar system, let's say beyond Jupiter, temperature is low enough that water can condense. Most people would put this snow line just before Jupiter, because of course Jupiter was beyond the snow line. Okay, and so that brings us to let's take a good look at the abundance of elements in the Earth. This is an exercise that some people like to do. You plot the abundance of the elements in the Earth normalized to the abundance of the elements in some undifferentiated material of the solar system. Most of the time we choose a carbonaceous chondrite, the infamous Ci. Ci is Orgueil, it's an I because it's Ivuna, it's a little brother of Orgueil here. And we have normalized to here, and here this condensation temperature, we have refractory elements, and we see that there is a declining concentration with a decline. So the Earth is depleted in all these elements. Does it mean that the Earth went all the way down to here? No, because as I told you before, if the Earth stopped condensing elements somewhere around here, let's say between 1000 and 1200 degrees, there should be no water at all, there should be no sulfur at all. I know that some people love to put a lot of sulfur in Mars. I think it's a total nonsense, because the sulfur is somewhere here, and if Mars stopped condensing here, I don't see why there should be so much sulfur in Mars altogether. So we have this very smooth trend here, okay, indicating that the Earth is fundamentally depleted in volatile elements. So now let's take a look at another problem, a related problem, which is the lunar giant impact. Bill Hardman's standard theory now that is accepted by nearly everyone. The moon was formed by having an impactor, the size of which is under discussion now, but the standard theory was that the impactor was the size of Mars. Someone liked to have it bigger, some other liked to have it smaller. Now there's some discussion. The jury is still out to decide whether it is possible or not, but the idea of the giant impact between two bodies and two similar bodies, which is documented by oxygen isotopes. We'll come back to this in a moment. But let's see what's going on here. Instead of having, during the impact, we form a lot of gas, temperature goes up to several thousand degrees, so a lot of the material is vaporized, melted. But the difference with the previous case, condensation out of the solar nebula, is that we don't have hydrogen. If we have a hydrogen, it's almost nothing. And if we don't have helium, we don't have any of this, okay? It's mostly iron, silicon, oxygen, and things like this. That's what it is. That's the composition of the lunar nebula when we are right here, and it's gonna be very difficult. So the difference is enormous, because now we have a gas, we have the same kind of a disk orbiting the Earth, with a lot of gas there. But this gas is made of SiO, it's made of Mg, it's made of OH, a little bit of OH, not much. It's made of all kinds of things. And you have, remind you, you don't have this term here. The total pressure is not hydrogen anymore. The total pressure is something which is highly reactive. So we're going to try to find out how to deal with this problem by looking at volatile elements in the moon. The way we do that is slightly different from the way I did. It was different from what most people did so far. There were some nice compilations. Remember that Apollo missions brought back something like 400 kilos of rocks, but among these 400 kilos of rocks, there is not a single sample of a material that we could consider as representing the lunar mantle. It's all the crust, it's all superficial materials, all basalts. You have accumulates, but we don't have anything. It's just like on Earth, we have no sample from the mantle. On Earth, we have samples from the mantle, but it's samples from the sublithospheric mantle. We don't have samples from the convective mantle. That's even worse for the moon, so we have to be smart to infer the composition of the moon. So if we take this is a very simple idea going back to Jean-Guy Schilling in 1980 and Al Hoffman in Mainz in 1983, you have this observation that the ratios of some elements doesn't change with the amount of one element or the other. Here is cesium, rubidium versus cesium. What does it take? Cesium is what you call an incompatible element. This is an element that nobody wants. You don't want cesium. Nobody does, okay? And cesium is rejected by most silicates, but most crystallized silicates. It's called an incompatible element. It's incompatible with the structure of the minerals. So when there is melting in the mantle, all the cesium goes into the melt. When there is crystallization of a melt, all the cesium remains in the residual melt. So this axis here is telling you, well, something is going on with magmatic activity, either crystallization or melting here. And you see that cesium rubidium doesn't change. So what it's telling you is that the magmatic processes don't change the cesium rubidium ratio in the melt, so it means that this cesium rubidium ratio is the ratio of the mantle source. Produce a basalt, and the basalt comes with the cesium rubidium ratio because it doesn't change during melting. It comes with the cesium rubidium ratio of the mantle, and it stays the same. Comes for whatever reason, so it doesn't change at all here. So we have this couple here, let's call them magic ratios, okay? And there's a number of them. And they are extremely interesting when we have pairs associating a volatile element and refractory element, like a potassium uranium, rubidium barium, cesium rubidium, zinc iron, and H2O. Zinc is a bit more compatible. Or water cerium. I'm going to develop this quickly here. So we have different pairs of elements with that kind of properties, insensitive to magmatic activity. You have incompatible elements. In blue, you have volatile elements. In red, refractory elements. Rubidium, barium, potassium, uranium, lead, cerium, volatile, refractory. You have the same kind of ratios for compatible elements, zinc, iron, germanium, silicon, although germanium goes into metals. It's a siderophile element. And another one, we really love this one, water over cerium. That doesn't change with the magmatic process. Now this is the work we did on the moon, and we plotted rubidium, barium. I compiled the high-quality data by this great man, Paul Gast, who died at the age of 43, leading the Apollo program. Some people forgot about this guy. And you have this high-quality data here, rubidium, barium versus barium here. This is one case. You see our meteorite should be very high, but the Earth is somewhere here. Okay, rubidium, barium doesn't change during magmatic processes on Earth. This is georock, this is mid-ocean ridge basalts plus ocean floor basalts, well, ocean island basalts. This ratio is more or less constant here. And you see that the moon is depleted. Well, you might have some difference between high titanium basalt and low titanium basalt because the moon is probably heterogeneous the way we'll see it. Potassium, uranium, same idea. You have in the meteorites, in chondrites, this ratio is something like a 60,000 on Earth. This potassium-uranium ratio versus potassium here is 10,000. Volatile, refractory. Remember, volatile, refractory here. And titanium basalt, high titanium basalt, and low titanium basalts are depleted relative to the moon, to the Earth. Same with zinc and iron. This is something I did with Cintilli and Emmanuel Albala, and you see that zinc is actually very depleted in the moon relative to the Earth. These are terrestrial basalts here. They're right here, zinc iron versus iron, or you could plot it against zinc, because if the ratio is constant, it doesn't really matter. And here are the lunar samples. These are laser ablation on some lunar rocks here. So zinc is depleted. So let's try to understand what's going on. Let's say, well, was the moon is clearly depleted in volatile elements. And so the idea, the very current idea, particularly led by one of my former students, I can disagree with, that the moon lost volatile elements during condensation here. We have to understand, we have to make a volatility scale independent of the original nebula volatility scale. Why? Because there is no hydrogen. So in order to understand that, this is the energy scale here. When you go from minerals to gas, here is the petrology. Petrology is mineral reaction. It's peanuts, doesn't count. Energy of mineral reaction is essentially zero. You can forget it. Okay, that's not very important. Then about 20 to 30% of the energy it takes to vaporize a material, okay, it's melting. And the rest is atomization. Is actually, you have a melt, and you have to break the bonds, and that's where the most difficult part of the job is. Breaking the bond between Mg and O, between Si and O, between H and O. That's where all the energy is. Okay, so you have to realize that if you take if it is an energy scale, it's dominated by atomization here. So why should we do this? It's not a very nice table. Here is to show you that the condensation temperature, the T50, depends on the hydrogen pressure. If you change hydrogen pressure here, is 10 to minus 4 bars of hydrogen, 10 to minus 6 of hydrogen. And you see that the temperature, condensation temperature changes here. Okay? The way I'm going to do it is to take the Earth, assuming that the Earth condensed out of the solar nebula, and try to calibrate this condensation scale versus another energy scale, which is not depending on hydrogen pressure. So I'm going to take a bond energy. You have all these elements with the bond energy here. Try to identify the possible ligands here. And I'm going to take the condensation temperature of the Earth for each element and plot it against the energy. Why am I doing this? Because you have a number of things that are very specific to the lunar disk. A lunar disk is made of silicate vapor. first, it should be less reducing than the solar nebula, which is chiefly composed of hydrogen. There's a lot of hydrogen in the solar nebula, so the environment is extremely reducing. On the moon, it doesn't look obvious to most people. The lunar disk is probably much more oxidizing than the normal nebula environment. Second, condensation of temperature of mineral phases depend on partial pressure of the elements in the cooling nebula, and therefore on the total gas pressure. If I make an Earth for myself, or Mars, my little Mars, if I make it out of the solar nebula, when I condense a little bit of silicon, a little bit of iron, a little bit of magnesium, I take it, the nebula doesn't even see it because it's mostly made of hydrogen and helium. It doesn't care. The total pressure remains the same. Hydrogen is totally insensitive to the condensation of planetary material. That's, terrestrial planets, okay? And the third point is the total pressure decreases when the moon forms with condensation because it's made of silicon, of magnesium, of oxygen. So you start making moon, the lunar mantle and the lunar core, assuming that there is a lunar core, I don't really know. But by precipitating silicon, magnesium, I decrease the total pressure, which is not the case for the solar nebula. So the logic is entirely different. People still applying condensation temperature. I see that every day, people applying condensation temperatures derived from the solar nebula to the moon formation is a total nonsense, of course, in this case. And if I plot, I check my scale. This is bond energy, the one I gave you, versus this is for the Earth. I can calibrate the bond energy versus temperature, the T50, the standard for the solar nebula for the Earth, assuming that the Earth has been made out of the hydrogen-bearing gas. Because of the original T50, the original condensation temperature. And as you see, it's not too bad, okay? This is a good correlation temperature. So essentially, the condensation temperature is an energy scale. This is nothing else, okay? And this is the energy of the bonds. So if I use that for the Earth and the Moon, this is what I'm getting here. So the same kind of plot as I showed you before, abundance normalized to carbonaceous chondrites and normalized to magnesium. For the same reason we normalize to calcium the abundance of volatile elements versus bond energy, and not anymore against condensation temperature here. Bond energy is here. In blue you got the Earth, and in red you got the Moon. It is a very consistent temperature scale. We read in a review early last year that condensation temperature is a mess. It's not a mess, okay? It's very regular here. You have these temperature scales. It means something that you cannot pick your own element and consider this element outside of the context of all the other elements. All the elements work together. They have the same logic. You cannot pick up water, you cannot pick up carbon and say, my water does this, and don't care about the rest of the elements. It is a very important issue. And here you have, I'm not going to comment on the details of this, but the Earth and the Moon. And you see clearly that not only the Earth is, the Earth is enriched, or the Moon is depleted in water with respect to the Earth, which is something everybody knew since the Apollo days. Not only this, but it's depleted in every single volatile element. And I don't see how you can get around that, okay? And don't try to isolate. So water is going to be a different case. Can we lose? So we have to wonder whether we lost volatiles during moon formation. The answer is no, and I'm going to tell you why. We have to understand how an atmosphere is made. Okay, this is the planet here. This is the elevation, the altitude here. This is the ground, And the atmosphere in which we live is an atmosphere with a high pressure. So you cannot lose nitrogen. If you could, even from the point of view of escape velocity, if you could lose a carbon or nitrogen or whatever you have, you cannot, because if let's say hydrogen tries to escape this room, for instance, before it exits through the door, it will meet millions and millions of other molecules. It will collide so many times that it cannot escape. So we have what we call the Maxwell-Boltzmann velocity distribution here. We cannot have loss of material from a planet as long as collisions prevent it. You have some special mechanism called the hydrodynamic escape, which is essentially having hydrogen kicking the butt of everybody to extract material with a heavy molar weight. But that doesn't I don't think that many people believe in that anymore. But if hydrogen is, but essentially you don't lose, and at some point the number of collision here is so small, is very small, and then one atom of hydrogen has a chance of escaping the atmosphere before it meets another guy. Okay, there is no collision anymore. This elevation scale is called the exobase. Okay, here you can calculate in different ways. And above this, it's non-thermalized. There is no Maxwell distribution. We don't have exchange of different degrees of freedom, and we can lose material. But of course, we can lose material from here, but there is nothing in there because the pressure is so low that there is no. So essentially what we have expansion here. This is what I drew, just so you understand. You have the core of the atmosphere, which is collisional, which is Maxwell type. And when there is expansion here, there is cooling, because we change the thermal energy into momentum, pure momentum, which actually we conserved with a change in enthalpy here, which is the most important here. And you can have some materials. Okay, so the controlling factor here is the height of the exobase here. How do you calculate the height of the exobase for the lunar disk? It's something which is done in a number of textbooks. You calculate, you have let's say you consider a molecule which is an atom which is located somewhere here. This is the Earth, so the gravity is somewhere here. Okay, shut up. Here we have the gravity going this way. There is a component in which is vertical relative to the equatorial plane. So there is some gravity here. We have to calculate this gravity factor. It's relatively simple mathematics here. Omega here is a rotation velocity here, and we can calculate. We can use this number here, which is the orbital frequency here, and we can calculate the exobase, the value of the exobase H here by calculating using the hydrostatic balance here, using that kind of number. G is the gravity constant, m is the mass of the Earth, small m is the mass of the atoms, T is temperature, and R is the distance here. So you have that kind of variation of pressure, and you can calculate the height of the exobase. Conclusion is that if you use the reasonable numbers, most of the material is concentrated below the exobase, and losing significant amounts of volatiles is difficult because you have to go to be above the exobase, but above the exobase there isn't much to lose anyway. Okay, and the process goes so fast. We formed the disk in a matter of days. It's not a matter of millions of years. We formed the disk in a matter of days. So the loss of material is something extremely difficult to achieve. So losing volatiles is different. And I don't know why I put it back. Well, another aspect that tells you that we don't lose the material from the disk very easily is to compare a number of elements with the same chemical properties but with different mass. You would expect that elements that are light are lost much more than elements with the same properties that are heavier. So if you compare halogens, fluorine, bromine, iodine, okay, you see that the heavy guy is iodine and is the most depleted. Fluorine is light and is less depleted. It should be the other way around. Same thing with sodium, potassium, rubidium, cesium, alkali elements here, okay? You compare rubidium, cesium, sodium, potassium, they're all the same. There is no mass, there is no atomic weight effect. So chances that it is the depletion is an effect of a loss from the lunar disk is extremely small. So we don't lose significant amounts of volatile from the moon during the impact. So let's go back to water and let's try to treat water by itself and emphasize some magic properties of water. And in particular is a magic relationship to one of the rare earth elements, a light rare earth element called cerium. So we have three rare earths that are next to each other: lanthanum, cerium, neodymium. Lanthanum is light, cerium is in the middle, neodymium is heavier. And Peter Michael in 1995 made this fantastic observation. Using the same type of plot, he didn't use neodymium or water here, but he plotted this ratio versus something that tells you something about magmatic processes. You don't care. It's a lanthanum, samarium, or niobium, zirconium. It tells you the effect of magmatic process. What did he find? Okay, he found that the water-lanthanum ratio goes this way. Water neodymium goes that way, and water cerium goes this way. This is telling us that water has the same geochemical behavior in magmatic process as water and cerium have the same properties. So we can use that to say, well, water is not fractionate from cerium. And you can see that in Jackie Dixon's PhD results or whatever. Water and potassium are correlated. Water behaves as an incompatible elements in magmatic process. So we can constrain water very, very tightly with this ratio. So we can use that. We know how much cerium there is in the earth. We know, and we can use that to figure out how much water is in the earth. Okay, we know how much water is in more, for instance, 0.1%. And we can use a 10% that we heard this number from Tillman yesterday for a 10% melt fraction. We can conclude that there is 100 ppm water in the Moab source in the upper mantle, which is okay. Or we can use this number, water cerium. We always get that kind of number, 200 to 500 ppm of water in the mantle, in the bulk silicate, and there is the equivalent amount in the ocean. So essentially, people like to say there is one ocean inside, one ocean outside. This is our best estimate. Be careful, we have absolutely no idea about how much water is in the deep mantle. There may be 10 times as much water in the deep mantle, and we will never know. Because it's soluble, we can put it, we don't know whether it's there or not. It's the same for carbon. We have no clue of how much carbon and water is in the deep mantle. We know reasonably what's going on in the upper mantle, but we don't know. Okay, so yeah, that's the table showing water and cerium ratio here in MORBs, in mid-ocean basalts. In you see these ratios, 200 is something we can use. So if you go back to the water-cerium ratio and summarize what you have, in chondrite the water-cerium ratio is 300,000. Bulk silicate earth is something like a 200 or 300, okay? And moon extrapolated from the trend I gave you is 0.3. It's pretty low. It's very dry, okay? There are some samples, and we're going to go back to this with with a much higher value for the moon. There's some pyroclastic material I'm going to talk about. They are actually some fire fountains. The way you can calculate the water in the moon is relatively simple. This is a daisy chain calculation that people like very much. Water in the moon is equal to water divided by cerium, cerium to magnesium, two refractory elements times magnesium in the moon. You cannot be wrong by more than a factor of 2 on this number here, and so you cannot be wrong by more than a factor of 2 on water in the moon. So there cannot be that much water in the moon if that way of calculating the values is correct. So you can say that some people measure water in the moon, and this is a paper by Chen from last year, this is water cerium here against, and you have using cerium value, you can calculate the amount of water in the moon. These are basalts, lunar basalts, and of course, and these are the pyroclastic glasses that Eric Carey from DTM and Alberto Sal from Brown measured over the last few years, and the problem is that they like to retain that value. Say, oh, the whole thing here is outgassed. We lost water from these samples. They like to keep this one here, but actually there are plenty of values that are very low, showing that we cannot make a decision for how much. But essentially retaining that there is something like 1 ppm water in the moon instead of hundreds of ppm in the Earth is something which is relatively reasonable, okay? And it's telling you that in some other places there is some water, like the source of these particular orange glasses, okay? You can have wet places which are interpret as being places where there is still. So where does that water come from? And I'm going to tie it in the theory of late veneer. Late veneer, which some people like to call late accretion, is the idea that, as was explained yesterday by by Tillman, planets, giant planets move and wreak havoc in the distribution of asteroids and planets in the outer solar system. So we have some redistribution of the material. And the way we have some material delivered to the Earth, we can calculate in a very simple way. We have some elements called platinum group elements. Whenever these elements see a speck of metal, of iron or nickel, they all go into here, okay? Geochemists would say the partition coefficient between metal and silicate is in the range of 10 to the 5th or 10 to the 6th. So whenever there is a trace of metal, all the PGEs, the platinum group elements, go into the metal, and there is nothing left in the silicates. That's idea number 1. Idea number 2, PGEs are nevertheless present in the lunar mantle, in the lunar and the terrestrial mantle. So if they're still present, assuming that the Earth has a core, which is a reasonable assumption, it means that these PGEs have been delivered after core formation. They came afterward. They've been delivered by something else. After core formed probably around 30 million years after the solar system formed. So we have these PGEs present in terrestrial and lunar mantle. They must have been added after core segregation. If we take the face value, the amount of PGEs, and assume that is the delivery of undifferentiated chondritic material, which is reasonable, it amounts to 0.4% of late veneer addition. 0.4%, let's say between 0.3 and 0.5%. This is reasonable. Another point is PGEs in the lunar mantle is a factor of 40 less than in the Earth. And that's something we don't understand, because the Earth is larger, so if there is material being delivered, of course you would expect that the Earth the Earth collects more because it has a larger radius, but is divided by the volume. So the cross-section for an object is a pi r squared, but you have to divide it by something which is pi r cubed for the volume. So the Earth should have less laid veneer in terms of relative contribution than the Moon. It's exactly the opposite we're seeing. Okay? There's a larger cross-section, but it's diluted in more material. So the idea is that this laid veneer explains a lot of things, and including water. And this is my suggestion, that the laid veneer of carbonation chondrite may account for most of water present in the Earth. We can do that by using this kind of ratio. Bit on enrichment, and should leave the terrestrial mean. Yes, the water. Okay, that's the same thing. Okay. So we have this. What kind of water can it be? Okay, now we're going to use another type of argument. Is a deuterium-hydrogen ratio. Some people consider deuterium-hydrogen ratio as a magic ratio, and it's not. It is a relatively simple process. It's a thermometer. Okay, the DH ratio. If you calculate a gas like the solar nebula, that was in the beginning, we go back in time. Okay, you have hydrogen, you have water everywhere, and the DH ratio here, DH in water divided by DH in H2. This is Jupiter, Saturn, Uranus, and Neptune here. Okay, if you take this is the fractionation factor between deuterium and hydrogen as a function of the distance to the sun here. Okay, you see that essentially the DH ratio is a thermometer. If you have a high DH ratio, means the material comes from outside of the solar system, and the DH ratio is small, comes from the inner part of the solar system. This is what it is. And we can see this with, this is the protosolar nebula. Jupiter collects without fractionating anything. Okay, Jupiter, Saturn here. They collect all the hydrogen, so there is no fractionation of deuterium here. You have the protosolar, and we have the sun here. The sun value is somewhere here, the DH ratio. The Earth is here, and we have the comets right here. This is why people didn't want to have a comets to bring water to. That was the original idea by Tobias Owen in 1995 to have water delivered to the Earth by comets. You would be swimming in cometary water, which is quite romantic, but it actually doesn't work in terms of DH ratio. Until we found this Jupiter type class of comets here, that's a little old. There is some more data. But essentially, we can see that chondrites and Jupiter type comets actually fit the DH ratio of the Earth. So we're going to admit that what accounts for water in the Earth and probably the Moon and the places is delivery from the outer solar system of objects coming from around Jupiter, places like this. No comets, but no primordial water. And this is something. Blue is wet and red is dry. This is Sean Raymond's famous movie. And you see that everything, we have a radial mixing, which, as I told Tillman yesterday, is a problem for the origin of material. But you see that there is some mixing, some radial mixing of the here. This is Jupiter here, and on the right here, you can see that something is going on. Okay, it's eccentricity, but you've seen this plot yesterday versus distance to the sun. Okay, and you see that asteroids are excited by Jupiter, and they collide with the inner part of the solar system, and you can end up with a fairly decent solar system, except for Mars, which is a discussion we had yesterday. Okay, you've seen enough of it. Let's try to understand the origin of this material. Very quickly, let me remind you some very basic principle. So we have isotopic composition. Delta is the deviation in per mil in general of the value of a sample with respect to a reference. The reference is the seawater. The abundance of 016 is seawater here, and is the deviation here. So you have two pairs of isotopes, 18O, 16O, and 17O, 16O. And for normal process, for normal geochemical process, this variation here should be twice that variation here. Okay, and this is what we call mass-dependent fractionation. And all the samples, that's called TFL, is terrestrial fractionation line, all the terrestrial samples and all the lunar samples plot on that line here, delta O18, delta O16, the slope is 0.5, and which is probably the major argument for the lunar giant impact. Okay, we have these things for the terrestrial, but not everything is plotting on this. You also have a mass-independent fractionation. You have a difference that cannot be accounted for by normal physical, chemical processes, evaporation, crystallization, sedimentation, tectonics, or whatever. You cannot move points outside of the TFL line here, the blue line. You need something else. Samples must be different from the different origin. The sun is something like a 50 per mil below the line. There is an excess. Okay, if you you can also see this cap delta O17 here, which is that value, which is a measure of the O16 deficit with respect to the Earth. And we can see that the sun has a 5% excess of oxygen 16 with respect to the rest of the solar system. We have a different material. We have a chondrites here, we have a Mars here, we have a eucrites here. So the solar system is not homogeneous. It comes from different material. Okay, you come from here, and the sun by itself is something which is very different from the rest of the solar nebula. This is the same plot here. And if I plot mass-independent fractionation versus mass-dependent fractionation, I can see that I must account for the solar nebula as a complex mixture of components that have nothing to do with each other. Well, for 15 years, people tried to explain this difference in oxygen isotope by a funny process called self-shielding. Self-shielding, when the solar nebula formed, CO, okay, was the dominant species of carbon. Just the same way as SiO is the dominant species of silicon, CO is the dominant species of carbon. And astronomers had pointed out a number of years ago that the absorption of UVs by CO is different depending on whether carbon is carbon-12 or is carbon-13. So the situation here is this one here. That's what you call self-shielding of solar UV by nebular CO, and that's very popular until a few years ago, still is among some people. But oxygen 16 being the most abundant species here, and O18 being the least abundant with oxygen 16, the optical thickness is different, and since they absorb in a different wavelength, you have a fractionation which is not mass dependent. That's the sense of self-shielding here. Let me go back to here. So you see that the absorption here is 16O, 18O, different here, 12 and 13 are different. You have different lines for absorption here, depending on which species you're focusing on. Okay, and that was this, I would say, the standard interpretation until for the year 2000. Okay, and people were fighting in meetings, and it would be. But now we have something else. We have this correlation of O16 excess, which is the cap delta O17, with Chrome-54. Chrome-54 is a neutron-rich isotope. It's goes back to nucleosynthesis. It cannot be changed during the formation of the solar system. It's inherited from the pre-solar history of the solar nebula. So it's clear that this excess of this neutron-rich form of Chrome-54, at least for carbonaceous chondrites, is related to cap delta O17. We have a number of examples. Titanium-50 is the same. Calcium-48, all these neutron-rich attest, if it was needed, that oxygen isotope variability is due to a pre-solar heterogeneity. So we don't have one nebula, we have a nebula A. Okay, and that's extremely important. And it's not even true, we hadn't realized that when we published this 10 years ago with Jean-Marc Luc, that we have this very nice correlation with the stable isotopes, normal stable isotopes. We thought that they were normally mass-dependent fractionation, but we had this correlation with copper and cap delta was 17 here. It's beautiful here, and it's the same with zinc. Okay, so it tells you that we have a different part of the solar nebula, and Laplace's solar nebula look like this. This is what all our dynamicists are playing with, whereas what we have is something like this, and we cannot have a lot. We can have some, but not a lot of radial mixing in the solar nebula when planets form. Okay, we have to come down on these models in which you exchange material from one place to the other. Otherwise, we will wipe out all the isotopic heterogeneity in the solar system. Is not well mixed. Okay. So now a last problem maybe I will be talking about is how much, I'm going to go back to the amount of solar, of late veneer we need to have in different parts of the Earth and Moon system. As I told you, if the water was simply brought by the late veneer, and we have a 0.4% veneer addition, we can calculate the amount of water we would have in the bulk silicate earth. We use chondrite here, osmium in chondrite, osmium in the silicate earth, and we multiply by the amount of water in chondrite. How much, what is the possibility for the amount of water here? You make that calculation here, which is simple mass balance here. We get 800 ppm here. This is a minimum value, and I'm going to show you why. And we have the lunar mantle here. We should have a 17 ppm. So we're going to have to deal with that problem. Why is it a minimum value? Think of what an impact does to platinum group elements. You have this guy hitting the Earth here. There is a lot of energy, and there is a lot of evaporation here, melting here. And here is the material that will rain back down onto the surface of the Earth and account for the excess material which is in the mantle, including osmium. Okay? Whatever osmium is in there is going to be seen in the terrestrial mantle because it's in the vapor here. But if there is osmium in the metal here, it's going to go into the metal, it's going to race down to the core, and you're not going to see it. Whatever metal is actually, if there is differentiation either predating the impact or during the impact, whatever metal is in there is going to entrain some PGEs down into the core, and it will never be seen again. So the 0.4% is whatever is here or is here. Okay, it's what is visible. But at the same time for water, all the water in the system is in there. So the amount of PGEs in the terrestrial mantle or in the lower mantle is just an underestimate of how much late veneer has been added to the Earth. So we can have probably up to 1 or 2% of late veneer addition to the Earth without actually figuring it out. And there was a paper last year, 2 years ago now, by Jacobson Morbidelli, who was actually going after my model here. And you see that the relatively late, they use a number of models. They want to date the age of the lunar impact. And actually, yesterday, Tillman reported on similar figures. And the data, as usual, the way they did it to date the lunar impact was to run a number of models. They have two types of models. They have Earth-like planets from classical simulation and the Grand TAC here. And they really have a lot of money, these guys. They ran all these models here. And the idea is the relative late accreted mass versus the time of giant impact. The idea is the later the lunar giant impact, the smaller the amount of late veneer is left to accrete to the planet. Okay, if you make the lunar giant impact at, let's say, 30 million years, there will be a lot of material left to accrete as a late veneer. If you accrete it at 100 million years, there won't be much left, and late veneer cannot be that important. So they ran this, and they constrain that by assuming that there is 0.4% late veneer, and they decided that the age of the lunar giant impact is 75 million years. But then, if you make it 2%, that's a different story. If you admit that the amount of late veneer is seriously underestimated, that we have more water in the Earth because we have water at depth, okay, you can get 2% late veneer, and you get something which is at 30 million years, which is something that Chin-Shu Yin and I suggested in 2002. So the age of the lunar giant impact is not settled yet in my mind. It is something, and I'm still in favor of an early event here. So why is the lunar and the Earth very different from each other? We can compare the amount of PGEs in the Earth and the Moon. Okay, reservoir divided by. So the primitive upper mantle, this is rhenium, osmium, iridium, ruthenium. As I told you, the expectation was that the amount of PGEs in the mantle, in the terrestrial mantle, would be less than the amount in the lunar mantle, and it's exactly the opposite. So the excess is enormous. Okay, the Earth receives 150 times, if you make a correction for everything, more late veneer than the Moon. And so Morby was fighting with this for years because his idea was you had this rain of small objects. You know, the late veneer was a rain of small objects, and so if you make a statistical approach, you would say, well, the Earth and the Moon should have the same mass balance. And actually, it's not. What is it telling you? It's that the impactor, what brought water to the Earth, was not a series of small objects, but it was probably one or two large objects that crashed. Something like a Ganymede or Europe crashing into the Earth would bring enough water to account what you observe today on the Moon. So the idea is that one of the satellites or one of these asteroids cruising around Jupiter was actually smashing into the Earth, but there was not a huge amount of small objects, okay, being added with the water here. That's the only way you can explain why the Moon has such a deficit of water compared to the Earth. Well, just a few words about where people found water in the Moon. These are pyroclastic glasses. They are lava fountains. You've seen these beautiful lava fountains in Hawaii. That's exactly the same kind of thing, you know. There's the orange glass that can be seen even from the orbit. That's the green glass here. And they're just a small, they're very different from Mare basalts. And these are the wet samples from the Moon. Okay, and that was a very smart idea from Eric Harvey and Alberto Sal to measure not in the glass, which was apparently outgassed, not in the glass, but in the magma reservoir. They measure water in melt inclusions. They have some melt inclusions in olivines. So there is a glass bead like this, and in the glass bead there is an olivine crystal, and the olivine crystal itself has a melt inclusion. It's a Russian doll, You have a glass, olivine, and the melt inclusion. And they measure within the melt inclusion, and they find a lot of water. Okay, that's very simple. And they found huge amount of water in there. I don't deny that. Up to 1,000 ppm here. So it means that these these lavas must have collected probably water on their way. I would say that water has been collected by these lavas migrating into the subsurface material that contain a lot of let's say carbonaceous chondrites, and they could pick up water on their way to the surface. I can argue on this. This is because the moon is dry. One thing that we should realize that there is water in the moon. You can see it from calcium phosphates. There are two calcium phosphates, the dry one and the wet one. The wet one, we all heard about, is called apatite. Apatite is only calcium phosphate on Earth. The first time we ever saw a dry apatite was in 2008 in ultramafic inclusion from Siberia. The dry one is called whitlockite or marylite, depending on who you're talking to. Okay, it's totally unknown on Earth. The dry one is marylite or whitlockite. It's a dominant phosphate on the moon. Just from that point, you should be able to tell that the moon is really dry. Okay? We can actually try to find some accommodation to explain some particular samples, but essentially the moon is dry. Okay, so the conclusion is that the Earth contains a lot of water. A ton of bulk silicate Earth contains 500 grams of water. But if it wasn't the Sun and Jupiter, it would be 200 kilos. The Earth was born dry in the hot inner solar system before condensation of water and other volatile elements. The 500 grams of ton of terrestrial water came late. Water is extraterrestrial. Late veneer and current water content of the deep mantle are underestimated. And interim report for the moon, as forcefully established by careful work on Apollo sample 70, the source of Murray basalts is dry, as established by Harry in 2000, and Sal, the source of unusual pyroclastic orange and green glasses, contain volatiles in excess of the surrounding mantle, but this doesn't make the moon a wet planetary body, and volatile and pyroclastic glasses were introduced into the melt inclusion upon emplacement of the melt into a shallow water-rich environment rich in carbonaceous chondrites and comets. Okay, thank you.